Newton sat under an apple tree. An apple hit him on the head, and just like that, we got the law of universal gravitation. It's a story we've all heard before. But do you really understand how gravity works? In this video, I'm going to break down everything you need to know about gravity. The truth might actually be a lot different from what you think, and even Newton himself thought the very idea of gravity was completely absurd. Let's get right into it. Why does the apple fall? It sounds like a simple question, but throughout human history, surprisingly few people ever actually asked it. Not because it's a trivial question, but because the answer just seemed too obvious. But there were three major turning points in history where someone finally stepped up to answer it. And the crazy thing is, every time a new answer came along, it completely wiped out the entire way we thought about the world before. Aristotle, Newton, and Einstein. Three brilliant minds representing three entirely different models of reality. And right in the middle of that evolution of thought, there was one massive puzzle that Newton spent years trying to solve. If gravity is what pulls an apple down to the ground, then why doesn't that exact same force pull the moon down right along with it? The first recorded answer we have today belongs to Aristotle. To really understand Aristotle's theory, we have to put ourselves in the context of the 4th century BC. There were no telescopes, no stopwatches, and absolutely no precise measuring instruments. The only tool these philosophers had was observation with the naked eye. And what the naked eye saw was always consistent. Stones fall faster than feathers, clay sinks, while wood floats, and fire always rises to the sky. Aristotle looked at that reality and established his own system of rules. The universe is made up of 4 core elements: earth, water, air, and fire. In this natural order, each element has its own natural place. Earth belongs to the absolute lowest center, while fire belongs to the highest point. For Aristotle, objects don't move because some invisible force is pulling on them. They move simply because they are finding their way back to their natural place. The apple falls because its physical makeup contains a lot of the earth element. It simply has to return to Mother Earth. For almost 2 millennia, not a single person seriously doubted this. It wasn't because our ancestors lacked intelligence, but because Aristotle's theory aligned perfectly with everything they could observe in their daily lives. This brings us to the first real lesson of science. A theory isn't rejected just because it's wrong. It is only rejected when someone is brave enough to ask a question that the theory itself cannot answer. The first person to truly shake Aristotle's system was Galileo Galilei in the late 16th century. Aristotle had claimed that heavy objects must fall faster than light objects. It sounds incredibly reasonable, but Galileo asked a very practical question: how much faster? Twice as fast? 10 times as fast? Is there an exact mathematical ratio here? Legend has it that Galileo climbed the Leaning Tower of Pisa to drop objects of different weights. This story was actually only recorded by his student Viviani, and there are no independent witnesses to confirm it. But what was absolutely verified in the lab was this: Galileo rolled balls of different masses down an inclined plane to slow down their motion and carefully measure their acceleration. The results completely stunned the academic world. Everything, regardless of whether it was heavy or light, fell with the exact same acceleration and hit the ground at the exact same time. This discovery wasn't just a minor tweak to Aristotle's ideas. It completely shattered a framework of thought that had dominated for 2,000 years. If heavy and light objects fall at the exact same speed, then the so-called tendency to seek the natural place of the earth element suddenly becomes meaningless. The universe, it turned out, had to be operating under a completely different mechanism. Summer of 1666. Isaac Newton was only 23 years old. Cambridge University had to shut down because a terrifying plague was sweeping across England. Newton was forced to pack his bags and return to his hometown of Woolsthorpe to self-isolate for 18 long months. It was during this period of solitary isolation that he laid the groundwork for calculus, discovered the color theory of light, and sparked his very first ideas about gravity. The story of the falling apple actually has historical basis. Newton himself recounted this to his friend William Stukeley in 1726 when he was 83 years old. Of course, the apple didn't hit him on the head like the popular myths tend to suggest. Newton described that he was simply sitting quietly in the garden, watching an apple detach from a branch, and started thinking deeply about the force that was pulling it down. Newton's question didn't just stop at, "Why does the apple fall?" He pushed his thinking much further. Does this force have a limit? If we climbed a taller tree, would that force weaken at all? What if we climbed the highest mountain in the world? What if we flew right to the edge of the atmosphere? And what if we flew all the way to the moon? Would that force still exist? And Newton came up with a hypothesis that was completely crazy. At the time, the force pulling the apple to the ground in his garden and the force keeping the moon in the sky were actually the exact same thing. This was the true monumental leap in human thought. The idea that a trivial event happening in a corner of a Lincolnshire garden and a massive celestial body 384,000 kilometers away were both governed by the exact same law of physics. Before Newton, no one dared to think like this. The heavens and the earth had always been considered two separate worlds, operating on two entirely different sets of codes. But if they are pulled by the same force, why doesn't the moon just fall straight down and crush the earth exactly like the apple? Newton's answer was absolutely breathtaking. The moon actually is falling. It is falling continuously every single second, every single minute. But at the same time, the moon also possesses an incredibly fast horizontal velocity. Imagine this. Every time the moon falls a certain distance, the curved surface of the Earth curves away by that exact same amount. The moon will never ever touch the ground, simply because the ground is constantly dodging it. Newton materialized this thought process with a classic thought experiment. Try placing a cannon on top of a mountain so high that it reaches beyond the atmosphere. If you fire it with a small amount of gunpowder, giving it a slow velocity, the cannonball will fall to the ground at a short distance. If you add more gunpowder, creating a higher velocity, the cannonball will travel further before hitting the ground. Now, what if he fired a cannonball with a velocity so great, so incredibly fast, that the curvature of its falling trajectory perfectly matched the curvature of the Earth's surface? That cannonball would fall forever, constantly falling through the endless void, but it would never, ever hit the ground. It has entered an orbit. An orbit is not a state of escaping gravity. An orbit at its core is simply an endless, continuous free fall. To turn intuition into science, Newton needed a language, and that was mathematics. In 1687, in his magnum opus Principia Mathematica, the law of universal gravitation was officially published. But it didn't look anything like the version you learn today. It was stated like this: gravity acts on all bodies, and it is directly proportional to the quantity of matter or mass contained in each body, and inversely proportional to the square of the distance between their centers. While the formula you are familiar with looks like this. This equation establishes three core principles that we universally accept today. First, the gravitational pull is directly proportional to the product of the two masses. The heavier the objects, the stronger they pull on each other. Second, the pull is inversely proportional to the square of the distance. Meaning if two objects are twice as far apart, the gravitational force becomes 4 times weaker. If they move 3 times further away, the force drops by 9 times. And third G equals 6.67 times 10 to the power of -11 Newton square meters per kilogram squared. This is the universal gravitational constant, an unvarying number in every single corner of the universe. But that brings up a question. If Newton only stated the relationship between mass and distance, what was the known value of the constant g when he published the Principia? The answer will probably surprise you. In his original law of gravity, such a constant didn't even exist. Newton never invented, never wrote down, and never once used the constant g in any of his gravitational theories. In the Principia, Newton focused purely on the relative masses of celestial bodies. That means he was just comparing their masses to one another rather than relying on an absolute scale. The reason behind this was that Newton supported atomic theory, the idea that all matter is made up of tiny fundamental particles, and he believed that the absolute mass of an object was tied to the number of particles it contained, because there were just too many particles in any given mass. Accurately measuring them was theoretically impossible with the technology of his time. Therefore, he figured he couldn't precisely measure the absolute mass of a celestial body. Instead, he used Kepler's third law, which again didn't require g to find the mass of natural satellites relative to the celestial bodies they orbited. So, if Newton never used the gravitational constant, where exactly did it come from? And how did it find its way into the equations we use today? The answer begins nearly 100 years later, from the mind of an ambitious English physicist whose ultimate goal was to weigh the world. Henry Cavendish was one of the greatest chemists and physicists of his time. He was notoriously reclusive and shy. He would often walk alone at night just to avoid being seen, and he even built a private staircase in his house so he wouldn't have to cross paths with his own servants, keeping himself completely isolated. But as withdrawn as he was also incredibly obsessive and meticulous. Cavendish achieved success in many scientific pursuits through extreme patience and dedication. He always pushed forward in places where others would usually just give up. Most of his mansion and the wealth he inherited from his affluent family were converted into laboratories, leaving very little room for a personal life. One of his biggest hobbies was improving scientific instruments, a trait that proved extremely useful in his quest to determine the density of the Earth. At the time, astronomers around the globe desperately wanted to know the Earth's density because it could be used to determine the densities of other planets and improve maritime navigation. Even though the Royal Society of London had established the Committee of Attraction in 1772 and tested the deflection of a plumb line near a mountain in Scotland to conclude that the Earth's density was about 4.5 times that of water, Cavendish was still unsatisfied with both the results and the committee's assumptions. He decided to tackle the problem himself and pondered over it for the next few decades. In 1797, he conducted his own experiment by modifying a device called a torsion balance, originally created by his late friend, Reverend John Michell. This device consisted of two small metal spheres suspended at the ends of a 6-foot wooden rod by a wire acting as a torsion spring, with two massive lead spheres fixed right next to them. The entire setup was placed in a sealed shed to block out wind and temperature changes. Cavendish stood outside and observed the movement through a telescope, using the light from candles placed just above. By measuring the incredibly tiny angle of torsion and the oscillation period of the spheres, Cavendish managed, for the very first time, to measure the gravitational force between artificial objects in a laboratory. From this calculation, he published his result. The average density of the Earth was 5.448 times the density of water. It's important to note that Cavendish never directly found the constant g, nor did he even know it existed. He didn't need it to calculate the Earth's density because the quantities just canceled each other out in the proportional expressions. But his experiment played a crucial role because it provided the very first method to actually calculate this constant. Nearly a century later, when the metric system was invented and the kilogram became widely used, the need to express physical laws in absolute units increased significantly. In 1873, two French physicists, Marie-Alfred Cornu and Jean-Baptiste Bai, finally and officially introduced this constant of proportionality into Newton's equation to fit the metric system. At that time, it was denoted by a lowercase f, and it wasn't until 1894 that the British physicist Sir Charles Vernon Boys found the true value of this constant. He did this by recreating Cavendish's experiment with far more precise instruments, specifically using quartz fibers, which increased sensitivity and shrank the device down by a factor of 10. The value that Boys calculated was G equals 6.661 times 10 to the power of negative 11 Newton square meters per kilogram squared. That is an astonishingly accurate number compared to the modern value. It was Boys who later proposed at the Royal Society that the symbol for this constant be changed from a lowercase f to a capital G. This idea gradually caught on, and by 1930, the gravitational constant G had fully become the universal standard in the scientific world. Looking back, even without the constant, G. Newton still managed to prove his inverse square law through an ultimate test with the moon. Astronomical data at the time showed that the moon was sitting at a distance from the Earth's center equal to about 60 times the Earth's radius. If Newton's inverse square law was correct, then the acceleration exerted by the Earth on the moon had to be weaker than the acceleration right at the surface, by a factor of 60 squared, meaning it would be about 3,600 times smaller. Newton sat down and calculated the actual orbit of the moon, and the two numbers matched with astonishing precision. This was the exact moment when a philosophical idea officially transformed into a rigorous science, when it could yield specific numbers, and those numbers remained unshakable in the face of physical experiments. The exact same equation neatly resolved the trajectory of a falling apple in a garden, while simultaneously dictating the cosmic dance of all the planets orbiting the sun. For the very first time, a single law erased the boundary between the heavens and the earth. However, Newton himself saw the limitations of his own throne. He could describe exactly how gravity worked with absolute precision, but he was completely powerless to explain why. Why could two objects attract each other across a vast, empty, and desolate void? The concept of action at a distance. The idea that an object here could instantly pull the strings of an object way over there without any connecting medium was something that left Newton himself feeling baffled and uneasy in his surviving letters. That lingering why was left hanging in the air, challenging the world of physics for the next 228 years. For over 2 centuries, Newton's law of gravity reigned supreme as the ultimate truth, accurately predicting the motion of almost every single celestial body in the solar system. But everything was completely turned upside down in 1859, when the French astronomer Urbain Le Verrier discovered a strange anomaly in the orbit of Mercury. While analyzing data of Mercury passing across the Sun from 1697 to 1848, Le Verrier realized that after every single orbit, the perihelion, meaning the point closest to the Sun on Mercury's orbit, was not standing still. It was shifting, rotating slightly forward, a phenomenon known as precession. According to the precise calculations of the time, this deviation amounted to about 43 arcseconds per century, something that absolutely none of Newton's laws could explain. To save classical mechanics, Le Verrier applied a mathematical strategy that had brought him massive success once before. Previously, by noticing anomalies in the orbit of Uranus, Le Verrier had used mathematics to predict the existence of a planet lying much further out, and that's exactly how Neptune was discovered. This time he proposed a similar hypothesis. There must be some hidden planet lurking between Mercury and the Sun, whose gravitational pull was disrupting Mercury's orbit. He named this phantom planet Vulcan. For decades, astronomers frantically scoured the skies for Vulcan. They even waited for the total solar eclipses in 1901, 1905, and 1908 just to search for it. But the results came back completely empty. The planet Vulcan simply did not exist. The world of physics plunged into a deep, dead-end crisis. Newton's genius mathematical system was officially powerless against the smallest planet in the solar system. To understand why Newton's calculus was powerless against Mercury, we have to look directly at the mathematical structure of orbits. In classical mechanics, when solving the motion of a planet around the Sun using the inverse square law, physicists do not use standard Cartesian coordinates. They switch to polar coordinates and perform a classic mathematical substitution setting, u equal to the inverse of the radius, or u equals 1 over r. From here, Newton's equation of motion in a central force field is written as a second-order differential equation with respect to the angle phi. This is a linear differential equation with an incredibly beautiful structure. The solution to this equation is simply the equation of a standard ellipse in polar coordinates. Think about the cosine function in that solution. The value of this cosine function repeats periodically exactly after the angle. Phi increases by a factor of 2 pi, meaning every time Mercury completes one full orbit around the Sun. Geometrically, this ensures that the ellipse of the orbit always closes perfectly. According to Newton's mathematics, after using this equation and subtracting all external perturbations like the gravitational pull from other planets or the wobble of the Earth's frame of reference, Mercury's intrinsic orbit must have a precession rate of exactly 0. It is not allowed to deviate even a tiny bit, but in reality, it still deviates by 43 arcseconds per century. Newton's mathematics had hit a ceiling. Remember this equation, because we will come back to it later. In Newton's view of gravity, there was still another issue. That is, gravity propagates instantaneously, no matter how far apart two objects are. For example, if one day the Sun suddenly vanished, the Earth would immediately fly off its orbit because the gravitational force would disappear at the exact same moment as the Sun. But Newton himself felt uneasy about this property of gravity, as he once stated that one body may act upon another at a distance through a vacuum, without the mediation of anything else, is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Going back to the vanishing Sun scenario, what if you were sitting in a spaceship in deep space, positioned exactly halfway between the Sun and the Earth? In that case, the light traveling from the Sun and the Earth reaches your eyes in the exact same amount of time, and you observe the vanishing of the Sun and the Earth flying away at the exact same moment. Your observation makes perfect sense. But what would your friend back on Earth see? Since light takes about 8 minutes to travel from the Sun to the Earth, but gravity is instantaneous, your friend would feel the Earth fly away a full 8 minutes before realizing the Sun had vanished. That is completely absurd, as an observer would see the effect happen before the cause. The person who resolved this paradox was Albert Einstein with his theory of relativity. Going back to the differential equation from earlier, everything was only resolved when Einstein stepped in and changed the very architecture of this differential equation. To maintain simplicity, Einstein inherited Newton's mathematical framework, but general relativity forced him to introduce a brand new relativistic correction term. The orbital differential equation now becomes, pay close attention to that last term, the presence of the speed of light c and the inverse square of the radius is the geometric footprint of a warped spacetime. This small but powerful term breaks the symmetrical periodicity of the old cosine function. The new solution to the equation introduces a parameter called sigma, representing the angular frequency shift due to relativistic effects. Now, the perihelion no longer occurs after every cycle of 2 pi, but instead it satisfies the condition. What does this actually mean? The mathematics shows that when Mercury finishes one orbit, its angle, phi, has passed the 2 pi mark just a little bit. It no longer returns to its original coordinates, but is pushed slightly forward. When putting the physical constants into the expression for sigma, the equation solves to a deviation of exactly 0.103 arcseconds per orbit. And when you multiply that by the number of orbits Mercury makes in 100 years, the cumulative total jumps to exactly 43 arcseconds per century, a perfect absolute match to what astronomers observed through their lenses. In 1915, Einstein officially published his theory of general relativity. This theory completely wiped out the concept of gravitational force as Newton understood it. Gravity is not some invisible force reaching its hand across space to pull objects together. Gravity, at its core, is geometry. The presence of massive objects like the Earth or the Sun warps and curves the four-dimensional fabric of space-time around them. Other objects moving through this region of space are not being pulled by any force at all. They are simply following the straightest, most natural path possible through a geometry that has been reshaped. In mathematics, the shortest path in a curved space is called a geodesic. The apple falls simply because it is following its own geodesic. And with that same warping of space-time, if the sun were to suddenly disappear, the space-time around it would snap back to its original state at a finite speed. It's just like holding one end of a string and giving it a whip. It takes a moment for that interaction to travel to the other end. Therefore, by the time the change in space-time curvature reaches the Earth, the light has already arrived as well. Because of this, our friend on Earth will see the cause and the effect at the exact same time. No paradox occurs. Looking back at this journey, we can see that today we use both Newton's and Einstein's formulas. Newton's theory is actually a special case of Einstein's when we look at environments operating at low velocities and weak gravitational fields. That is why in most practical engineering applications today, from building bridges and roads to launching rockets and calculating satellite orbits, engineers still use Newton's formulas because they are simple and accurate enough. But for more complex systems, we are absolutely forced to account for Einstein's relativity. Take GPS, for example. The stretching of time caused by gravity would cause the positioning on your phone to drift by kilometers after just one day. These two theories do not conflict with each other. They are simply used under different levels of complexity. And that is absolutely everything you need to know about gravity, from its different explanations to why the formula we use today looks the way it does. If you found this video helpful, don't hesitate to give us a like, leave a comment, and make sure to subscribe to the channel so you don't miss any of our latest videos.